Well, hello and welcome back to Engineering 201 Electrical Fundamentals, and I want to pick up where we left off last time with our introduction to AC analysis and continue on doing this and basically an overview of what we're going to be looking at next term. Not going into probably as much depth as we will next term, taking a few things for granted, not going into the derivations and whatnot, but kind of seeing more and learning more about this AC analysis. Well, last time we looked at something that we could represent with a sine or a cosine, where we said that some function x of t might be equal to some amplitude times the sine of omega t plus some phase shift theta. And I don't know that we talked about it last time, but remember that omega was equal to 2 pi times the frequency f. And a lot of times we see f being around here 60 cycles. 50 and 60 are a couple of big numbers throughout the world. There are other frequencies, but a couple of the big ones are 50 or 60 cycles. So if you multiply 2 pi times 60, you come up with 377. So a lot of times we'll see 377. Not always. If you see something different, they're just running at a different frequency. But if you see 377, wonder, well, where in the world did 377 come from? That's what's going on there. So we could, if we wanted to, express maybe a voltage as some amplitude. We just take 300 times the sine of maybe that 377t plus the phase shift, and that would be an angle in there. Or we could have current as some amplitude, maybe 10 times the cosine. And remember, we talked about the only difference between the sine and the cosine was a phase shift. We'll shift those back or forth 90. And we might have it at the same frequency, 377t plus, usually we use the phase shift phi for that, whatever that angle might be. Now you can imagine as you start working in problems with this, if we might need to add these and subtract these, divide by these. If we're going to have a capacitor and inductor in there, we'll probably be integrating these or differentiating these, and that's not particularly easy to do with an expression like this. So this is what we call the time domain. So in the time domain, this looks like a sinusoid. Okay, so we have time here. What we want to do is we want to use complex numbers. We want to use Eulers Equation. And Eulers Equation, and that is spelled with an E, Eulers Equation is that E, the base of the natural logarithm, taken to the j omega t, is equal to the cosine of omega t plus j times the sine of omega t. Okay, and the Euler has lots of equations. I think I talked about last time, but that's one of them, and the one that we're going to use. Of course, this portion here is real, and this portion here is imaginary. Now remember that j is going to be equal to the square root of -1. Probably learned this in math, that this was I. We have I, enough I's for current, so we're not going to think of that as I, we're going to think of that as J. So if I were to think of then, let's say, some voltage, V of t, being equal to some magnitude times the cosine, and I'm going to start to base this off of cosine because of this term here, cosine omega t plus theta, I could really write this as the real portion of Euler's equation, which would be V sub m multiplying then e to the j omega t plus theta. Okay, so I use Euler's equation to take the real portion of that, and I come back to what I started with. And this looks a little awkward to work with, but what we will very quickly do is put this into phasor form, where I can say that I have some magnitude at some angle theta, which is much easier to work with. So this is a phasor. And if you're looking in printed material, it will be done with a bold. Okay, so you'll see a bold like that. No one wants to watch me write a bold, so we'll just usually put a dot over it, and it can take on different forms, or it'd be a current phasor and whatnot. And what this really is the real portion of a complex number. It's the real portion of a complex number. So if I start to look then at phasor domain, in the phasor domain, we will look at it like this, where we have a real, and then in this direction I have imaginary. Okay, instead of spelling or abbreviating imaginary with a G, I actually put a J. Okay, I realize that should be a G, imaginary, but I put a J because that's in the J direction, so that's the imaginary direction. So we would have this, it would look something like this, with the magnitude Vm at some angle theta. Okay, so oftentimes we will be given a problem in the time domain. We will switch it into the phasor domain to do the work, because it's a lot easier to manipulate these things. We'll really just treat them a lot like vectors. They're not vectors, they're the real portion of a complex number, but from a mathematical standpoint, we're going to manipulate them and work them a lot like vectors. And then we can switch them back and give the answer again in time domain. So what do some of the elements look like in time domain? So if I look at a resistor, what's that look like? Well, we're going to have this term what we call impedance. Okay, the impedance, and the impedance of a resistor is just equal to R. Okay, and impedance, we use the symbol Z, and it shows up, we write it like a phasor, but it's actually a complex number because the impedance has a real portion, which happens to be the resistance, plus J times the complex portion, whatever that might be, usually the capacitance or the inductance. Okay, so what about then for an inductor? What is Z equal to? Well, Z is equal to J omega L. Okay, and what about for a capacitor? What is Z equal to? Well, Z is equal to 1 over J omega C. So remember when we said that a inductor oftentimes had a lot of built-in resistance. So you have L and you have R sub L. Well, if we look for the impedance for this whole thing, this is where we would say that the impedance would be equal to R sub L. That's the real portion plus J omega L, right? That's the reactive portion there. And we're going to talk about terms like that, reactive. Next term we'll go into a lot more definitions. We'll actually go through the derivations of these two. For now, I think I'm just going to put those down there. We'll take them a bit for granted, but when we start next term, we'll go through the derivations of this so you can trust where those came from. One thing that you'll probably see is that this is also equal to minus J divided by omega C. Oftentimes we express it like that because it's a little easier to work with. And you might say, well, how in the world did you get the J from the denominator up into the numerator? Well, remember when you have a complex number, we could show J is a variety of things. J is the square root of minus 1. We could say that that's equal to 0 in the real portion plus J1 in the imaginary portion. And we could even say that this is equal to 1 at the angle of 90 degrees. I mean, J goes by a lot of different identities. And I'd like to pick this one. So if I say that I have 1 over J, I could really say that that's equal to 1, which is really 1 at 0, divided by 1 at 90. So I'm using that one right there. And when I divide complex numbers, I divide the magnitude. So that's going to be 1 at an angle of 0 minus 90 So I get 1 at minus 90. Now if I go on to the complex plane, so I take this under the complex plane, where this is the real, and this is the imaginary. Okay, 1 at minus 90 is down there. What would be another name for 1 at minus 90? That would be minus j, wouldn't it? So that's how we can come up with that one. Now, if you're manipulating complex numbers and whatnot, if you're saying, huh, what's going on here, if that's a little fuzzy, let's talk a little bit about that. There's a few things I've glossed over that maybe we need to talk about. I didn't spend much time on Eulers equation. That's a pretty cool equation. But let's look quickly at how you manipulate these complex numbers. Let's say that we have a complex number in rectangular form. So I'm going to say that I have a plus jb plus c plus jd. And I want to add those together. Well, that would simply be equal to a plus c. I add the real portions, and then I add the complex portions, b plus d. I mean, to some extent, when they taught you that 2 plus 2 was equal to 4, they didn't tell you the whole story. This would be 2 plus j0, and 2 plus j0. It gives me 4 plus j0, right? Just happens to be I have real numbers. All of this is 0 over here. So if we're adding and subtracting, and I guess I could say add and subtract, we get something like that. And if we're adding and subtracting, we really would like the numbers in a rectangular form. That makes life a lot easier. And for that matter, if I look at this on the real and the imaginary plane, how can I get a number from a rectangular to a polar form? If I take the number a, there's a in the real, and b in the imaginary, there it is on the complex plane. So could I get the magnitude? Yeah, there's the magnitude. And probably shouldn't have put the magnitude there. I should have put it up there. There's the magnitude. And here is the angle theta. So we could convert from some rectangular form, a plus jb, to some magnitude form, some polar form, m, at an angle of theta. And could you convert back? Sure. And it's simple right triangle trigonometry. And really, I don't want to commit heresy here. I don't want to keep talking about vectors too much, but if we've got a vector in a Cartesian form and we want to go back to a polar form, it's the same math. Well, what if you have a vector that you're wanting to multiply or divide? So let's look at these in a polar form. Let's say I have magnitude 1 at some angle theta 1. And I'm going to divide that. I guess I'll do division first. Probably should do multiplication first, but we'll get through this. And I take another complex number that has magnitude 2 at some angle theta 2. And what's that equal to? Well, it's going to be equal to the ratio of their magnitude. So I divide m1 by m2. And what do I do with the angles? I subtract the denominator. So theta 1 minus theta 2. So that's how I divide two numbers. If I want to multiply, so again, let's say that I have magnitude 1 at theta 1, and I want to multiply that times m2 at theta 2, what's that turn out to be? Well, I multiply, find the product of the magnitudes, m1 times m2, and then what do I do to the angles? I add them, theta 1 plus theta 2. Okay, so let me double check that. I've divided and subtracted. Here I have multiplied and added. So I think we're good. So what if you have a vector that is in a polar form, a magnitude angle form, and you want to add it? Well, you're probably going to have to convert it into a rectangular form. What if you have something in a rectangular form and you want to multiply or divide it? Again, you're probably going to have to convert it. And I think it's important that we be able to do this, we be able to understand what's going on behind here, but eventually we're going to turn this over to our calculator because it can very quickly make all of these things happen for us. Well, like I said, maybe I didn't spend enough time oohing and ahhing over Eulers equation. I think you'll see pretty quickly how useful it is. There's some other neat things as we're passing by that equation. what if we were to, let me double check this sheet here before I, R J omega L, yeah, I think we're good with that. Now we're going to come back and use these, so you'll want to remember those. Well, let me hop back and look at Eulers equation here. And trig identities, I can never remember all the trig identities that I need to. Here's kind of an interesting use of Eulers equation. Remember the trig identity cosine of alpha plus beta is equal to the cosine of alpha times the cosine of beta. And then, is that a negative? I don't know. Is it a negative? Is it a positive? Because the sign is the other way. Sine alpha, sine beta. And now remember the proof of this was not particularly easy. Well, we can go through this very quickly with Eulers equation. So, and this is a bit of a side. Maybe we could put a tangent. We'll say this is a tangent up here, but it shows you the power of Eulers equation. And really, I think Euler is really underappreciated at times. He did a tremendous amount of work at a very young age. But anyway, we could say that the cosine of alpha plus beta is equal to the real portion, so I'll just say the real portion of e to the j alpha plus beta, which would give me the real portion. What could I do with this e? I'm going to break that up, and I'm going to say that's e to the j alpha times e to the j beta, because when you multiply, you add exponents. So I could say that this is the real portion of the cosine of alpha plus j sine alpha times the cosine of beta plus j sine beta. So here I used Euler's equation to go from this to this, and again then I used Euler's equation here to go from this back to there. So I've used Euler's equation twice here. So when I go through multiplying this, I'm looking at the real portion of what? I'm going to have cosine alpha times cosine beta. And then I'm going to have plus j sine alpha cosine beta. I guess I'm okay with that. Yeah, j sine alpha cosine beta plus cosine alpha j sine beta. It would have been a little better to do those in opposite order, but I think that's okay. And then I have what? J squared sine of alpha sine of beta, don't I? Let me double check that here. Yeah. Okay. So let's see. This is definitely imaginary. Okay, and I read imaginary with a J, so remember it's the J. This is definitely imaginary. Well, what about J squared? Remember that J takes on all these funny names. J equals square root of minus 1, so J squared, that's equal to what? Minus 1, isn't it? So this is actually real. So this is real. And this being minus 1, so this is real. So I could say then that the cosine of alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. Okay, so indeed, let me double check this here. Excuse me. Indeed, we did show that that was a negative sign, and that's because square root of minus 1. So, kind of interesting. I don't know that we're going to do things like this in electrical, but to show you the power of Euler's equation. And while we're on that subject, it's kind of neat. We don't want to confuse this with Euler's identity, but you'll see people talking about Euler's identity and what was that? You'll see Let's see. Eulers identity is e to the I pi plus 1 is equal to 0. Maybe, you hang around certain types of people. You'll even see someone, I've seen someone with a tattoo of this. And I'm not recommending you get a tattoo of this. But well, if you already have a tattoo of this, I'm not saying that's a bad thing either. So anyway, Eulers identity, and we're not going to we're going to use Eulers equation a lot. We've already talked about Eulers equation, but this is kind of neat, and again, shows you kind of how cool Euler was. You have all the neat pieces here. You have the base of the natural logarithm. You have pi. You have the square root of minus 1. You have 1, and you have 0. All of those are really neat pieces. Let me change this a little bit. Something we recognize, e j pi plus 1 is equal to 0. So I guess if you are going to get that tattoo, you're going to have to figure out whether you're going to prove that you're a math geek or whether you're an engineering electrical geek, whether you use J or whether you use I. But anyway, we'll get back to the math part of this. If I go and look at the unit circle, and a lot of times we're going to go to the unit circle and look at this thing. And to some extent, when we have been going to the real and the imaginary before, we've been going to the unit circle, haven't we? Well, anyway, if I look at e to the j pi, I could use Euler's equation and say with Euler's equation, oops, there I did it, tried to spell Euler with an O. Using Euler's equation, I would have the cosine of pi plus j times the sine of pi, so I'm using Euler's equation on that term, plus 1 is equal to 0. What's the cosine of pi? I'm over there, aren't I? So that is minus 1. Plus j, what's the sine of pi? That's 0. Plus 1 is equal to 0. Indeed, 0 is equal to 0, isn't it? So Euler's identity, certainly interesting. You can appreciate that probably more now. Well, let me check on a couple things here. Okay, I think what we will do, we've got all of that done. Let me tackle a couple of problems then. Some of these you'll probably recognize maybe from the homework problem, so worth going through some of these. So let's say that you've got some AC system here, and you are given that you have some voltage across here, V of t, and that is going through some resistor. We'll say it's a 12 ohm resistor, and you have some current I of t. And we're going to say that if V of t is given as 10 times the cosine of 377t plus 80 volts, we'd like to ask the question, what is I of t? Okay. So I'm going to do what I do in most cases. I'm going to convert this into phasor form. I don't want to have to deal with this in time domain. We've got time domain here. I'm going to go into phasor form. So in phasor form, I would say that this voltage would be equal to, interesting, at 60 cycles. I would say it would be 10 at 80. Okay? And that's still volts. Okay? I lost that it was 60 cycles. I don't know that anymore. Okay, and we'll see how that affects circuits in the future. But for now, I leave that like that. And then I can go and I can look at Ohm's law. Remember Ohm's law that V is equal to IR? Well, we're going to replace this. The new Ohm's law, we're going to say, is now that phasor voltage V is equal to phasor current I, times the impedance Z. Okay, so phasor voltage V is equal to phasor current I times the complex number, the impedance Z. Okay. Well, what's Z for the resistor? Well, we know that Z for the resistor, that's simply just 12 plus J0. I mean, it's 12. It's a real number. Or you could really, if you wanted to, say that this was 12 at an angle of 0, couldn't you? So then if I want to solve for the current, I take this thing and I say that the current I is equal to the phasor voltage V divided by the impedance. So what do we have? I have 10 at 80 divided by 12 at 0. So what's that going to turn out to be? 5/12. Give you a number there. 0.83 at an angle of 80 less 0 is 80 amps. Okay? 80 amps. But I want the answer in time domain. I'm not done yet, so I got to convert this back to time domain. What's this look like in the time domain? Well, in the time domain, the current in the time domain is equal to the magnitude 0.83 times the cosine. I based it on a cosine function. There's a frequency, 377. That hasn't changed. That's one thing. All our problems, they'll be the entire problem will all be the same frequency. Then we might go to another problem and be a different frequency. But everything in this problem is going to be the same frequency. Won't be till next term when we start looking, or excuse me, not next term, but spring term, when we start looking at things that are, we have different frequencies going on. So we've got this. Well, maybe I better pen that comment. I think it's the latter part of winter term. We touch on that and we get into it in earnest in spring term. But anyway, so this whole, suffice to say, this whole problem is 377. So I put 377 here. I'll have T, and then what's my phase shift? 80. Okay, and that's amps. So this is in the time domain. This is in the time domain. Well, what's this in the phasor domain? This is kind of interesting. Because there's the real, there's the imaginary. Where's my voltage? 10 at 80, right? Okay, so there is 10 at 80. So my voltage phasor is going to look something like that. Where's my current phasor? 0.83. They're in phase, aren't they? So we'll find out that a resistor allows the current and the voltage to be in phase. They're in phase here. If I were to look at this in the time domain, these would be rising and falling at the same time. They might have drastically different amplitudes, but they would be rising and falling at the same time. They would be in phase. Okay. So I think that's good for that. Let's try another problem. We'll try one more for the day. And let's say that we have an inductor. So again, I'm going to say that I've got some system here. I've got an inductor. I'm going to say it's a really good inductor, that I don't have any resistance. So it's probably not true, but maybe the resistance is very small compared to the inductance. I'm going to say that the inductance is equal to 1 millihenry. And I've got some voltage across here, V of t, and I would like to solve for the current I of t. And I'm going to be told that maybe my V of t is equal to 5 times the sine of 377t minus 90. Okay, and that's going to be volts. Okay, and I would like to find what I of t is. Okay, the first thing I'm going to do is I notice that all of a sudden I'm given a sine, and I could actually work the problem in sine and then get the final answer in sine. Sometimes that can have problems. I think probably I'll be consistent. We're going to start getting in a habit of always just working things in cosine, always working them in cosine. So let me convert that. How could I convert that? I could say that that's equal to what? Well, my trig identity says that I just need to subtract 90 degrees. So I could really write this as what? 5 times the cosine of 377t minus 90. That comes from that, and then I also have to subtract off another 90. That's my trig ID. And go between sine and cosine by adding and subtracting 90 degrees. So if I put this in phasor form, if I put the voltage in phasor form, I have a magnitude of 5 at what? Minus 180. 5 at minus 180. So again, I go back and I look at phasor voltage V is equal to phasor current I times the impedance Z, or that I is equal to voltage V divided by impedance Z, right? Well, what's Z? And we know for this thing that Z has to be equal to J omega L, which is going to be equal to what? J, what's omega? Right there, 377, times L, 1 millihenry. 1 times 10 to the minus 3, right? That's where that comes from, 10 to the minus 3. So this turns out to be equal to, what is that? 1 times 10 to the minus 3 just is J at 0.377, isn't it? Okay, and that would actually be ohms. So I can use that now in here. I can say that my current I is going to be my voltage, which would be 5 at an angle of minus 180 divided by the impedance, which is J at 0.377. Okay, J at 0.377. I got to figure out how to do that. Well, let's see. 5 at minus 180. This J is really 1 at 90, isn't it? So couldn't I say that I have 0.377 at 90 degrees? Yeah, that'd be the same thing. So now when I get this, I'm going to come up with, what is that, 13.3? I'll double check that. At an angle of minus 180 minus 90. I mean, we might think that this is minus 180 minus 90 would be minus 270. Okay. Probably, if you have a calculator, maybe I'll just throw it into the calculator and give this a try. When it comes back with the answer, it said that it was equal to 13.3, that's good, at an angle of 90. Whoops, is there a mistake somewhere? Well, a lot of times when people ask for help on their homework or something, I'll sketch a unit circle. And they'll have something like this. I'll say, I think it's this, but the answer is this. Well, let's see who's right. Maybe both people are right. We've got the real, the imaginary. 13.3 at minus 270. So minus 270 is clear around there, isn't it? So 13.3 at minus 270, or 13.3 at 90. There's 13.3 at 90, isn't it? It's the same thing. And this is really the preferred answer. Okay, that's going to be in amps. So you'd have 13.3 at 90 amps. And actually, probably if you key this in your calculator, this is another one to think about, 5 at minus 180 is really going to be minus 180. That'd be the same as 5 at 180, or minus 5, right? So lots of ways to express that. Well, we want this answer in time domain, so we could say that this is in time domain equal to 13.3 times the cosine of 377t plus 90 degrees. And that's amps. And if you wanted to go back into a sine form, you could do that at that point if you want to. I don't know that we have to. I'm just going to go ahead and leave it like that. Okay. Well, I think We'll double check that here. I think we're good. That gets us to a nice stopping point. Next time, we'll look at one more circuit with a capacitor, and then we'll start to look at what happens when you have combinations of these. And that will get us to probably a pretty good stopping point. We don't want to tackle all of next term before we end this term. I'll probably have a little bit of a review, and that should wrap up the term. So we're getting close. Keep on working hard. Work on your complex numbers. There's an appendix usually at the back of the textbook that talks about how to manipulate, how to work with complex numbers if you've forgotten, so take advantage of that, and we'll talk next time. Take care till then, and thanks for watching.